see that.
Real time screen. Okay?
Yeah, okay. So, Professor Jean-Paul Blejo from Saclay is our next speaker. Yeah, Professor Blejo, please.
Yeah, well, thank you very much for this kind invitation. It's a real honor and pleasure to be not here in person, but to be able to express to Vikash my greatest and warmest congratulations for his achievements. I think I've got to know Vikash about the same time as Harry, that is after the Asgama meeting. And the meeting which actually I kept in my mind is this first ICPA PGP meetings that the Vikash organized in Mumbai. This was the beginning of the field. At that time, we were all excited by the first results of coming out of the SPS. It was very, very preliminary pieces of data. But it was a very, I still remember vividly the discussion, the physics discussion we had at that time. It was also an occasion for me to meet not only Vikash the physicist, but Vikash the music lovers. And I remember that he had organized a fantastic Indian music concert at this occasion, and we had the opportunity to discuss about Indian music. See that meeting, I had many opportunities to come back to India and develop collaborations which are still going on at the moment. And part of the material that I shall discuss with you soon involve actually people from Indian institutes. So, again, congratulations, Vikash. It was a very, for all what you've done. Let me turn to the physics program. What I want to talk about is a question that has been very much discussed in the theoretical community over the last 10, 15 years, essentially since the beginning of Rick. And it comes from the experimental observation that hydrodynamics work amazingly well in describing the evolution of matter produced in heavy ion collisions. And it works so well that in some cases one wonders why this is so. And this is part of the type of question that I would like to discuss in a very simplified context. So typically, fluid behavior requires some degree of local equilibrium that goes under the terminology of thermalization. And the question is, how is that achieved? And whether this is achieved at all. So there's a useful picture that follows from general physics considerations is that the microscopic degrees of freedom relax quickly towards local equilibrium, while long wavelength nodes, which are associated typically to conservation laws, relax on much longer timescales. And that's a basic way we understand how hydrodynamics emerge in various contexts. I'm going to focus on kinetic theory later on. There, the microscopic degrees of freedom will be described by a distribution function. You can think of it as a distribution of quantum with momentum p and located at space-time point x. And the transition from this microscopic description to the macroscopic description involves macroscopic fields which are typically energy density and some pressures. And the conservation laws, which are associated with energy and pressure, is just the conservation of energy momentum density, which is summarized here in this equation. So, let me say a word about thermalization. There are two basic aspects which are involved here. One is a rearrangement of momentum shade in momentum space. And to make things more clear, I have here plotted the distribution function. This is f of p versus momentum. And the typical initial distribution looks like the blue curve here. And that blue curve is typically what one gets in pictures of initial states like the color glass, for instance. And the third distribution that the system is expected to evolve to is indicated by this red line, which is Bose-Einstein or Fermi-Dirac or whatever, at efficiently high temperature. So I'm not going to be concerned by this aspect of the problem. This is interesting in itself. But I am going to summarize what goes on in the radial momentum distribution by just keeping the p-square average. That's enough to describe energy density and pressure, as we shall see in a moment. And this will be described quantitatively and systematically by a special set of moments which I have selected. The thing which I want to focus on is another aspect of thermalization, which concerns the shape of the momentum distribution. And that will be the main topic of the talk. You know, when local equilibrium is reached, or close to be reached, the momentum distribution, because there are collisions, for instance, in the system, tend to become isotropic. If it is not isotropic, there are currents which develop in the system, which try to make the momentum distribution isotropic. And the reason why this is interesting is that there is a competition. There is a competition between effect of collisions, which tends to make momentum distribution isotropic, and the rapid expansion of the system, which is dictated by the condition of the collision. To see that more quantitatively, let me draw the following picture here. It is a momentum space distribution that follows from free motion of the particle. If you are in a collisionless regime, the collision axis is the z axis, so the map which is produced has been produced by collision of two nuclei moving in the z direction. And after a while, the particle which have a large pz momentum, they will escape the collision zone. And what will remain after a while is just a momentum distribution in which only low pz particles survive. So this effect, which is rather trivial, is just mostly kinetical, can be quantified by introducing two different pressures. A longitudinal pressure, pz squared p naught, p naught being the energy of the particle, so in which this is pz times the velocity along the z direction, and similarly in the transverse direction, and in the direction x and y. I will refer to this as longitudinal and transverse pressure. And a measure of the anisotropy of the momentum distribution can be expressed in terms of the difference between these two pressures, longitudinal and transverse. And what has been found in many calculations is that this anisotropy relaxes slowly. It relaxes in very much the same way as a collective variable which would be associated to a conservation law. Of course, there is no conservation law associated with this particular quantity, but its relaxation remains very slow. And the first hints from that phenomenon came from holographic description, namely ADS-CFT type of calculation. I want to show you here a slide from the paper by the Polish collaboration, Heller, Yannick, and Witasik, in about 10 years ago, where they calculated where the microscopic theory here came from this ADS-CFT correspondence. So this has to do with solving the Einstein equation with various initial conditions. And this is represented on the left figure by these numerous black lines, which you see are sensitive to initial data. But what is remarkable is that after some time, the measure of the time is this variable W here, which is proportional to the proper time. you see that all these curves merge into a unique curve, independent of the initial condition. And if you want to translate this result in terms of something which is directly related to pressure and isotropy, this is Pt minus P over the energy density, what you see, one of these solutions here is represented by the black curve, and the other solution, the other curve represents results of hydro calculation, which can be done exactly in this molecular context. And you have a first order, second order, third order hydrodynamics. Now the important point is that, which was a puzzle at the time, was that hydrodynamics starts to work when the pressure asymmetry measured by this quantity is of order 1, it's 0.6, but it's large. So we are still far from local equilibrium, and still this hydrodynamics seems to work pretty well. Another observation that is also present on this figure is that you see that when first order stops to work, second order doesn't do much better, and third order neither. And I will come back to this issue of trying to improve hydrodynamic description a little bit later. The important point here that I want to retain is that there is a kind of apparent history of why hydro starts to work when the pressure isotropy is mentioned. Okay, so to address the question, I'm going to go into a simplified, idealized picture, which is pretty commonly used in this particular context. Namely, I'm going to use Bjork and boost symmetry. I'm going to consider a collision at very high energy, where the produced matter is, to a good approximation, invariant under Lorentz boost, which means that essentially all what happens along the longitudinal direction can be related to what happened in the central rapidity slice by symmetry. So, to make the story short, in other words, the distribution function, which is dependent on 4 space-time coordinate and 4 momenta, becomes a function of a proper time tau, a transverse momentum, and a longitudinal momentum. And I want to analyze the evolution of the system under a simple kinetic equation, which was first written down many years ago, I guess in the early 80s by Goldberg, and which describes the kinetics, I mean the evolution of the distribution function under the effect of collisions, which are described here by a simple relaxation time approximation. So this, if you would ignore this term here, which I will come back to in a second, you see this equation just describe the relaxation of the momentum distribution towards the equilibrium distribution, which depends only on the energy and the proper time. So there are 2 regimes in this equation that you can guess without doing any calculation. The first regime is a short time regime, where the time, the observation time is small compared to the time between the collision. It's relaxation time to sub-R. So this is a regime which I will qualify as collisionless, particle just free stream. And then there is a regime which is dominated by the collision at late time, time is large compared to this collision time. Then we expect the system to go towards hydrodynamics. So let's say one word about the collisionless regime. The solution of this equation without the right-hand side is simply given by this equation here, which just transcribes in terms of the formula the physical phenomenon that I was alluding to earlier. If you let the particle free stream for some time, and the momentum distribution becomes squeezed in the z direction and becomes a flat pancake of that shape. Okay, so now, of course, this equation can be solved exactly on the computer, and I'm going to make it look very complicated at first, and but I'm not interested in numerical calculation. I want to understand how precisely things evolve. And to do so, I'm going to consider moment of the momentum distribution. So this is standard techniques in kinetics. And in the standard argument is that usually you don't care about the information which is contained in the momentum distribution. You're just interested in some global observable, like the energy density or the pressure. And the second thing, I want to focus on angular degrees of freedom. So I'm going to consider a very simple moment, which are given by this equation here. These are angular average, if you wish, of the momentum distribution, weighted with p squared, and only p squared. In most works, on 99% of works on kinetics using moments, you will meet moments in which all possible tensorial structure will appear. This is because in most of these works, one intends to reproduce the full momentum distribution. And in order to do so, indeed, you need all these particular tensors. But here, I'm not so much interested in the momentum distribution itself, but just its shape, and therefore I average everything with p squared. That's the argument I was reading earlier, that I'm not interested in what's going on in the rate of momentum direction. Well, this is easy, and only two moments will count. One which corresponds to P0 is equal to 1. This is a spherical average of F. This is the energy density. And the other is a quadruple deformation of the momentum distribution. And as you will see, as it is written here, actually, this is precisely BL minus VT. And the strategy now is to look for an effective theory for L0 and L1. I mean, for massless particle, which is the case I'm considering, the energy momentum tensor depends only on two independent quantities, which are precisely these two quantities, L0 and L1. Okay, so the effective theory is easy to build because we know the exact equation. This is the equation which is written here. And by taking the angular, by integrating this equation, I'm sorry, integrating this equation over angle with suitable version of the polynomial, we end up with an infinite set of equations. These are the equations written here. The first equation is the equation for the energy density. This is a standard evolution equation. The coefficient A0 or C0 are not, are just reserved for energy momentum conservation, so these are pure numbers. And the AN here in the other equation are also pure numbers, which are dictated by the longitudinal expansion. The last term here reflects the effect of the collision, and this is a damping of all the moments, the exponential damping of all the moments due to the collision. So this equation, if you solve that exactly, it will not allow you to reproduce the full momentum distribution, but they will give you the exact value of the energy density and the collision. And in this equation, as I was also saying, the separation between free motion, which is this complicated kernel here, and the collision is made completely transparent. Of course, this is still exact. And if you want to build an effective theory, you have to do simplification. And the first simplification which comes to mind, and which turned out to be, in fact, very good, is to drop all the moment except for L0, L1. So the equation for L1 would be the same as this one, in which I will drop the term N. For instance, what it is. So now we get what I call the two-moment rotation, the two-coupled equation for L0, L1. And what I want to argue, I will do that in the next slide, that all second-order discrete hydrodynamics versions, at least as I tried keyword, are incorporated in these two statistical equations. It's also a way to write hydrodynamics. It's not usually written as a coupled problem, but this is, I will show you in a moment, completely equivalent. And the solution, I mean, this simple 2x2 matrix problem actually hides a very rich mathematical structure, which I'm not going to describe, but just to use a few keywords, the notion of attractor, the gradient expansion and its divergence, the summation of the gradient expansion in terms of cross series. All this can be worked out analytically, and this is actually quite beautiful. But this is not going to be, I'm not going to discuss this, but this is another topic. So the point I want to convince you is that these simple equations actually provide a very accurate description of the kinetic and the transition to hydrodynamics. There will be, what is mentioned here, a renormalization, but I will come to that a little bit later. I mean, it's not, I mean, some of the coefficients here can be modified, and will explain to you why this is so. So let me first briefly present you how hydrodynamics emerges, hydrodynamics equations emerges from this. So we have the first movement equation, so these are exact. And if you knew what L2 is, you would be able, by solving these two equations, to get exactly L0 and 1. I'm going to drop L2, as I said, for the moment. Then the hydrodynamic fields are easy to identify. This has already been done. L0 is the inertial density, and L1, which is the difference of pressure, is usually the hydro literature called the viscous pressure, and the relation between the viscous pressure pi and the difference of pressure is explicitly written here. So if you go at late time, you extract the viscosity, because L1, the distortion of the momentum distribution, is going to be done. And in fact, we can convince ourselves that L1 has a gradient expansion. The gradients in this particular context are just the factors of 1 over time. So now, if you assume that L1 has a gradient expansion, L1 is about the 1 over tau. This L1 being 1 over tau can be dropped in front of 1 over tau. L1 over d tau can be dropped as well. And then you get a relation between L1 and L0, which is written here, 0 epsilon. And that's nothing but the viscous direction, where eta is the usual shear viscosity, which is expressed here in terms of the microscopic parameter. And if you stop here, then you do have hydrodynamics, which is usually referred to as first order, but this is a Navier-Stokes equation, which is different. If you want to go beyond that, you have to improve the gradient expansion. But in addition, what Israel and Stewart did in a bunch of